I'm Parashar. I'm the product manager with Vertex AI. And with me, I have Ugo and Jake. Today, we will talk about embeddings and take you to the fascinating journey of what embeddings can do. Let me first start with an overview. So in real life, you're actually using embeddings every time you do a Google search or look for a video or try to find a product on your famous or popular e-commerce websites, right? So every time you do that, you get some results back. And have you ever wondered, like, how is it able to get you relevant results all the time? Or how is it able to recommend you products that you might like, even though you may not have actually looked for that product before? Right? So that's the magic of embeddings. What embeddings are, it's basically numerical representation of this data. Now, the data can be text, image, video, any type of complex data. But what embeddings will do is convert these data into dense vectors of numbers. And then it will have similar vectors in the same vector space. So what I meant is if you have men and women and then king and queen, then man and king are in the same vector space. And similarly, women and queen are in the same vector space. And at the same time, king and queen are also in the same vector space. So while embeddings helps you convert this data types into numbers, when it's translated into vector space, these vectors are close to each other. So it preserves the meaning of the underlying data, right? And if the data is similar, like I gave you the example just now, then it will be closer together in the vector space. If it is dissimilar, then it will be farther apart. So the distance between these vectors can help you figure out, are these data related or not related? And that's how you are able to get very good product recommendations or search results, or you are even able to figure out use cases like fraud detection, which looks at dissimilar data, right? So if there is an outlier, essentially, you figure out there is something unusual going on, and embeddings will help you do that, right? Now, let's look at a couple of demos here. So I am in YouTube Music, and I'm just trying to see which particular artists I like. So I start with Bollywood artists, and then you can see in the recommendations, you actually get Bollywood artists. But as soon as you change to pop music, then the new recommendations are for artists representing pop music. And so now, as a user, I am mapped in a vector space where I like not only Bollywood music, but also pop music. And so if there is another user who is also having similar tastes, then the music recommendations could be similar. Okay, so that's one way to look at it. Now, let's take a look at another example. And in this example, I'm trying to find a table which is white in color. So I found a table which is brown, and then I take a picture. And then alongside that picture, I say, I want a white table, right? So now what is happening is image and text are working together, and because they are mapped in the same vector space. So now I'm able to not only do text-to-text mapping, but I'm also able to do text plus image-to-image mapping, right? And this goes on, like, because now you can also do video-based vector embedding, right? So when let me just switch to the next slide. Sorry. Yeah. So when I look at what Google Cloud Platform offers you, we have two different types of APIs. So the first one is Text Embeddings API, which helps you convert your textual data to embeddings. And the second API is Multimodal Embeddings API, which helps you convert your text, image, and even video into vectors. And the beauty of this Multimodal Embeddings API is now you are able to represent text, image, and video in the same dense vector space, which was not possible earlier, because prior, what you would have to do, and we'll see some examples as well, is probably have some keywords associated with your image or caption associated with your image, even have your video, like the audio in the video, to be transcribed, and then do some conversion. And so it was a complex workflow. But now, with multimodal embeddings, you can just call the API, send your image, video, or text, and then you can get vectors out of it, right? Now, the Google Cloud APIs for text embeddings allows you an output of up to 768 dimensions. What this means is, like say you have to represent a particular paragraph or a sentence in the vector space, then these words are converted into vectors, and even though these words would have individual vectors, when they are converted into this vector space, it preserves the meaning of the whole sentence. So the sentence, all the words in the sentence are actually co-located, and that's how you can you can enable scenarios like semantic search, where you're not just looking at the word, but the underlying meaning of that, right? And you are also able to do product recommendation, and I mentioned also fraud detection, right? So that is the text-to-text embeddings piece of it. And then, if we move to the multimodal embedding space, the Google Cloud Platform or the Vertex AI API for multimodal embeddings, it allows you up to 1,408 dimensions. And so what I meant is 1,408 vector representation of whatever your input data is, right? And what this does is it maps your text, image, and video in the same space. And it allows you to enable a new set of use cases which were earlier possible, but a little bit difficult to realize and probably less accurate, whereas now it's easier and also more accurate, right? And then you can use a combination of both. So depending on your input data, if it's text only, the recommendation is to use the text embeddings API. And if you have a combination of text, image, and video, or image and video, or just video, then the recommendation is to use the multimodal embeddings API. Okay? Now, what are we launching today, right? So I'm very excited to share that we are launching 2 new models for our text embeddings API. These models are launched in public preview, so you can actually start using them today. They are available for anyone to use. It's equivalent to our version 4. So we already have version 3 in GA, and it's performing great. But this one takes the performance a notch higher. So now we are ranking amongst the top in the MTEB leaderboard. And Ugo will walk you through what MTEB leaderboard is later on. And then along with us being in the top of the leaderboard, we are also introducing a new feature we call as dynamic dimensions. So traditionally, what happens is when you have to map a particular type of data into vectors, you would use fixed dimensions. So in some cases, you may not need that many dimensions. Like say, if you are just trying to classify cat and dog, or animal and bird, you could probably do away with fewer numbers, right? Like in this case, probably it's 4 categories you are trying to do. So you don't need 768 dimensions vectors. So in scenarios like this, and I'm trying to simplify it, but in scenarios like this, what you can do is you can just probably use 256 dimensions, or even lower, like 128 dimensions. So now that is possible. And when you do this, traditionally, you would have loss of quality. But now, with support for flexible dimensions, you no longer lose quality. So depending on the type of data, how complex it is, what are your quality-related requirements, now you can use fewer dimensions or more number of dimensions. And this enables you to actually preserve storage and memory, which is expensive because you are storing these vectors in a vector DB, and it's expensive to do that. So by using fewer dimensions to represent the same data, now you are using less memory, less storage, and also less compute. So it's more compute efficient. So you can decrease the cost of storing these vectors. And the reason this is important is, imagine you have thousands and thousands of documents which you are embedding. Even even a few cents per word or something like that will actually translate to hundreds of dollars of saving for that vectors. And you have to keep on doing embedding often. Like every time your data changes, you may have to embed that entire database again, or a delta of that database again, depending on what scenario you have, right? So this translates into a lot of savings. So to summarize, with the new models, now you get much better quality, and we are beating our competition even with a smaller model. So with 768 dimensions, this is the best model in the world right now. There is no other model which is for embeddings which is at this level with 768 dimensions. The other models which are there, they either have higher number of dimensions or are larger in size, right? So that's very fascinating. And related to that, we do have a research paper which we published last week, and we also published a blog yesterday. Okay. Now, we are not just stopping there, right? So we did a lot of launches last year. And we are continuing to do that this year in Q1 and going forward. So last year, during Next, we launched the initial versions of text embeddings. Then we launched preview of our multimodal embeddings. In March, we went GA with multimodal embeddings for video. And today, like I mentioned, we are launching new text models. And going forward, we'll continue to improve the performance of the underlying models, and we'll also introduce more enterprise readiness features like compliance, Sec4, and things like that. And some of you, like I was at the booth yesterday and the day before, and some of you came to me and wanted to customize this embedding. So we also allow you to customize the embedding. So now you can actually create your own custom embeddings model by providing 50 to 100 samples. So it's supervised, but that tuning is also supported. And we have discussion on tuning later in the talk as well. Now, before I switch, I just wanted to show you a quick demo of the MTEB leaderboard. So this is the MTEB leaderboard, and like I said, Hugo is going to talk more about it. But we are here, number 5. So this is our model, Google Gecko Text Embeddings. And when you click it, essentially you see everything in our documentation in terms of how to use it and what it enables and things like that. Now, going back to the slides, I want to share a little bit more on the use cases that you can enable with embeddings and how you would do that. Right? So this is a simple architecture, a two-step process on how to use embeddings for something like semantic search. Right? So the first step is you have all your data in some storage, and it could be Google Cloud Storage. And then you would use the embeddings API. Depending on the data, in this case, it could be text only or text plus image. You would use the text embeddings API, or you would use the multimodal embedding API. And then you will store these embeddings in a vector database. And step 2 is whenever you have a query, you will convert that query in real time by calling the same embeddings API into a vector. And then you would do something as simple as similarity search on top of that vector DB, right? And then you'll get rank results. And the same concept can be even applied to other use cases. Of course, the type of comparison or the similarity score that you would perform would be different. So fraud detection would look for dissimilarity, but product recommendations, search, and things like that would look for re-ranking, similarity, and depending on the use case, like whatever you are trying to do, right? Now, let's go a step further. So multimodal embeddings for video. So in this case, what you would do is, just like you did for text and image, you would embed all your video in a vector DB, and then whenever you want to have like any semantic search on top of this video, then you would again embed that into using the multimodal API, embed it again into embeddings, and then compare it with your vector DB, right? Now, the beauty here is you don't have to do anything like object detection, speech recognition, or anything with video classification like what you would do in a traditional scenario. But instead, just call the embeddings API and have that video embedded, right? And right now, we support any length of video. So even if you have 60 minutes, 120 minutes, 2 hours, 3 hours, doesn't matter. The only thing you have to do right now is send 2 minutes chunk of that video to the API. So for a 60-minute video, what you would do is you would call the API 30 times, right? And each time, you will have a timestamp, like 0 to 2, 2 to 4, 4 to 6, and so on. And then you can get all these embeddings and then store it in the vector DB. Now here, we also give you a flexibility that depending on how dense you want this embeddings to be, you can actually pick how many embeddings are generated per minute. So you can do 4 embeddings per minute, 8 embeddings per minute, or 15 embeddings per minute, depending on how complex the video is, right? So we give you that flexibility to do that. Now, let's take a look at a demo where I'll show you multimodal embeddings in action. So here, I have a website. This we have built it for the demo. And this uses exactly the same multimodals API which I showed, and it's built on top of vector search, and the architecture is what I showed earlier. So what we have done is we have embedded all the videos, and then now when I put a query like show me a car with license plate 681, right? What it's doing is actually going into that search database, and in this case, what you could imagine is this could be your own enterprise data in the backend, and you have this search enabled, and then it gives me result of cars with license plate, and in particular, there is one with 681, right? So you can see here, this video has no audio, so there is no transcription, and it's actually just the license plate, which is 681, and from text to video, I can quickly do the search. So I mean, we are very excited to enable these kind of scenarios across different modalities and also provide a very high quality embeddings model. So with that, I'll switch it over to Hugo to talk about the embeddings in the financial domain.
Yeah, thanks, Parashar. So we'll take a look at a number of use cases within financial services where embeddings are applied. We'll look at 4 use cases. The first is information retrieval. In this use case, a lot of firms decide to build knowledge assistants that their frontline workers can use, and they augment it using the RAG pattern. The key driver here is that they want the answers to come from the internal corporate sources. So for example, there could be a new regulation issued by a regulatory body, like the SEC or FINRA, and they take these regulations and create policies that guide what their workers do. And they want this assistant, which is a chatbot or conversational search, to provide the answers from these policies that they've created. And so what they do is create an embedding, and we'll look at an architecture later, but they create an embedding space and use that with the power of the LLM to drive the conversation. The next use case is one that Parashar mentioned, fraud detection. Now, the beauty of this is you can choose whatever properties you want to embed. You can take either the location of the transaction, information on the transactional parties, the actual transaction itself, and embed those and start to do things like detect outliers or clusters. So you could identify that any transactions matching a certain pattern are probably suspicious, and you want to kick off a second level of action like alerts for suspicious activity or a phone call or some kind of authentication. Now, the beauty also of it is that as things change, because obviously fraud patterns change very quickly, you can start changing what you embed in your vector and react accordingly. The third one is just capturing insight from alternative data, which could be text or video or audio, like we just looked at. And you can use this embeddings to go through things like earnings reports, regulatory filings, and determine or find out certain things. So for example, you could notice that over time, certain things have been mentioned, not just particular phrases, but synonyms related to that phrase over time. And you could use that as an indication that there's a trend that you want to pay close attention to. The last use case we talk about here is personalization, which is fairly common. With this, you just embed properties of the user, so whatever you're interested in, and use that to drive how you react to the customer or the user. So things like someone logs in to their, let's say, brokerage account. You can suggest articles they may want to look at, depending on certain properties, or things they may want to keep track of. So we'll walk through an example of an architecture for information retrieval. This builds on what Parashar showed earlier, but a little more complex. In this case, let's say they were using their internal policy documents. They have a corpus or corpora of this document stored somewhere, and they feed this through embeddings to capture what they need. And those are now stored in a vector database. Now, the great thing about vector databases is we provide multiple options. We provide vector search, BigQuery, AlloyDB, and there are also other databases out there that you can use. But typically, your end user will come in, work with, let's say it's a chatbot, and let's say they're on a call or they're preparing for a meeting with a customer. They go in and ask a question like, how do we handle this thing about 401ks? And through a chat, the embeddings capture the right document, the right paragraph or sentence or page, and they can now pull out that information and react to it and provide answers. The next architecture we look at is fraud detection. With this, simply capture as much data as you have, which institutions tend to have a trove of data. It's a matter of how much insight do you want to derive. And you embed these. And so as I mentioned, it could be, what was the last location? What's the home location or address for the payer? What's the size of the transaction? It could be something that you flag and realize that over time, this is an atypical pattern. They don't typically spend in this manner. And those are all captured and put into your vector database. And so anytime there's a transaction, you simply call against that index, and using spatial recognition, realize that this is an outlier and needs to be flagged, or it's similar to these other fraudulent transactions. So transition to talking about benchmarking. One of the things that happens with just the explosion of different models is we're faced with this first question of how good are these models? You don't just want I call it an intuitive sense of it. You want an objective way to determine, like we just mentioned that we came out with a new version or an updated model. You want some way to benchmark this and say, OK, it's better than the other one, and it compares this way with the other models out there. And so industry-wide, we have a number of benchmarks that are used. There's GLUE, the General Language Understanding, which just basically pulls together a number of resources and in sentence pairs to determine the effectiveness of a model. We have SQUAD and we have RACE, and in this particular case, MTEB, which deals with embeddings. And we'll look at that in a little more detail. And so let's switch to the demo, and I'll kind of walk through the MTEB benchmark. And so the great thing about the MTEB benchmark is that there's this understanding that you don't just want a general benchmark that says this model is good. You're actually using it for various tasks. You're doing things like semantic search, similarities, and you want to find out, does this work against this? You also want to find out that, OK, this model is great, but is it really effective? Is it something that we can use at scale? Yes, it could be great, but requires so much computational resources that it's not workable. And the MTEB captures all of that. And so if we look at a series of the tasks, we see things like the model size, which gives you an idea of what the computational effort is required for it. You see how much memory it uses, the embedding space, and then the different tasks. And so it provides a score for things like classification, clustering, and you can now start mapping to not just this model is at this percentage on the leaderboard, but it actually performs well against these tasks there. And I'll just highlight ours. I think Parashar talked about it earlier. But the number 5 is the Google Gecko embedding model. And you can see both the size, the memory it takes, and how it performs against the different tasks there. And describe it. So I'll talk through it, just add some more context there as well. The MTEB is 56 data sets, covers 112 languages, and 8 tasks. The tasks include things like it's extensible, which is great. So as you have a new data set, all you have to do is feed it against the API. And like Hugging Face provides an API and a structure for the data, and you can go against that and run your benchmarks fairly quickly. And on that note, I'll reach out to Jake to come in and just talk about how 2 Sigma apply this.
Great, thank you, Ugo. Hey everyone, my name is Jake. I'm a product lead at 2 Sigma, which is a large quantitative hedge fund in New York. We do a lot of work with NLP. Today I'm going to present on kind of a demo case of how you might work through working with embeddings and fine-tuning embeddings. One thing I want to call at the start is Lance Dang, who's a QSE at 2 Sigma, helped pull together some of this material. So just, as a PM, credit where credit is due. Great. So today we're going to think a little bit about domain adaptation. So a lot of the things we've just talked about are general. They're trained to be general. They're pretty useful generally. In this case, we're going to kind of build a little sample application, which is a semantic search and RAG over some financial documents. So the idea is we put in a query, we get back the documents that we might be looking for. And the question we're asking is, can we improve our retrieval accuracy by using Vertex AI text embeddings and fine-tuning those embeddings? So as we said before, we're going to use the MTEB data set, and we're actually going to use a subset of that, which is the FIQA 2018, which is just focused on financial investment questions. These are Q&As from Stack Exchange. They're posts from 2009 to 2017. It's about 6,600 queries, 57,000 documents, and 1,700 document relationships. OK, so that's what we're going to evaluate against. But when we're fine-tuning, we may have some kind of data that's outside of the benchmark that we want to fine-tune with. In this case, we've picked another public data set. And internally, we would probably use something more proprietary. In this case, we're using MS Marco, which is a large Q&A data set, again, generated via Bing questions. And then we use human-generated answers. So they've kind of been filled out. It's not just the query results from Bing. One of the things that's really important when you basically are using this training data is to filter down for the specific domain. In this case, we've filtered down to business and finance-related queries using custom logic. I think something kind of fun about this is that we did use Gemini Pro to do that filtering. We asked, is this query about business and finance? We then filtered that out. And then we kind of did a sampling over that. So we end up with about 20,000 query document relationships over 100K documents. Great. So then fine-tuning. I think this is both the most interesting and probably the easiest part of this process. We use Vertex AI. We use the Gecko 003 embedding model. We set a batch size of 8, about 5,000 iterations. For GPUs, we use 4 V100s, and it took about 3 hours. We then hosted this model, again, within Vertex AI, using just a single A100. So what are the results here? OK, so some of you may not work in search or be as familiar with search metrics, so I kind of want to explain kind of what we see at the top line. The first metric is accuracy at 10. So this is a recall metric. So we send in the query. We get back 10 results. We then score those results on similarity. If we think that they meet the benchmark response, we just give it a binary 0 or 1. So if you have a query, you get back 10 responses. 7 of them are good. You have an accuracy of 0.7. NDCG is a little bit different. It is scoring on this kind of accuracy metric, but it's also discounting based on positionality. So you can imagine one scoring where at the first location you have a correct result, and the second one you have an incorrect result, and another scoring where you have an incorrect result and then a correct result. We will, in this kind of discounting, score the first one more than the second one because it was a little bit better at getting the top ranked result to be the correct one. So you can imagine a scenario where your accuracy is actually quite good, but within that accuracy, you're actually quite poor at doing the ranking within it. So just for a comparison model, I just put up the Gecko multilingual 001 model. We can see that it performs worse than both of the other two models that we're talking about, even though this is a multilingual data set. The baseline model that we used was the Gecko 003 data set. We can see that it performs decently well in accuracy and NDCG, but again, can we do better? So the last result is the fine-tuned model, which is based on the Gecko 003 model, but includes the 3 hours of fine-tuning we did with a very quick pass on a public data set. And here we see an 8% improvement on NDCG with just 3 hours of fine-tuning and an increase in accuracy. So I think in summary, kind of like, what did we kind of learn from this kind of experimentation? We've been doing larger and larger scales. I'm just doing an easy example because I can't share necessarily everything that we do day to day. But embeddings have made search and text retrieval tasks much improved over kind of more common methods you might have seen like 10 years ago in the space. I think we're really excited about the text embedding model capabilities. I think we talked about one earlier in terms of these dynamic dimensions. So you can basically train your embedding model. You can start experimenting with a higher dimensionality. You may go to production and someone says, hey, have you done the numbers? How much is this going to cost every day? The latency is low. You can then make those dynamic adjustments over time. So you're able to kind of make these memory storage and computational decisions post fine-tuning instead of pre-fine-tuning. We're really excited about multimodal embeddings now with video support, as we said earlier. Kind of this unified representation of video, image, and text data, I think, is actually a fairly big deal. If you are in a space where there is not a lot of labeling that exists, i.e. caption data for video or for annotations for audio, it really allows you to do some kind of innovative cross-modal use cases that weren't available to us before. Or if they were available, you need to have an NLP expert who was kind of very deep in the understanding of how to do these kind of cross-modal comparisons. I just showed a really easy example with the benchmarking. It's a well-understood benchmark, and we had some opinions on how we would like to score it. I would say that the more and more specific your use cases get, the more and more nuance you'll need to take to thinking about what is the benchmarking data I'm using? Is that actually useful? How am I scoring it? And then also, how do we trade off, right? I gave you an example where we increase metrics across the board. Unfortunately, that is not always the case. So you kind of need to bring your own expertise to these kind of model questions. And I think finally, and most importantly, just the bare minimum of a domain adaptation, something that literally took us a week to do, was almost a 10% gain over baseline, kind of the benchmark that we were doing. And so we see these leaderboards, we see number 4. That's very exciting. I think when you think about your own domain, the data that you're bringing to the table, your expertise in kind of doing that evaluation, I think the opportunity is actually much larger than we might think normally.